Welcome to this second tutorial in our mini series about the 555 timers. In this tutorial, we are going to be going over the monostable configuration. So in the last one, we just went over very briefly what's going on inside and kind of the different ideas. In this one, we are going to be going over that one of three normal configurations for a 555 timer. Now, the monostable configuration is where the 555 timer wants to settle into a certain state. So you push a button, it goes high, and then depending on your RC constant, it stays high for a certain amount of time, and then it drops back down to being low. And that's where the monostability, there's only one stable point in this circuit. That's where it wants to be. So today we are going to talk about that. We're going to get quite in depth, talking about what's going on inside. If you're just looking for a quick circuit diagram so you can put something together for your own experimentation, go check out our website where we have the circuit diagram. That'll be a lot faster and you can just put it together and it'll be really easy and straightforward. This is to understand the why it switches from 1 to 0 and why it's dependent on that RC time constant and why it acts the way it does. So it's going to be quite exciting, and we're going to do that conceptually. We're going to go through the circuit itself and the different states that it goes through. And then once we're done with that, we are going to do a practical circuit right here where we turn on the oscilloscope and we show actually what's happening with the output and with that timer circuit. And so it's always fun to see things in action. With that, let's jump straight into the circuit configuration. We'll briefly show what it looks like, and then we'll go into how it works. So this is your typical diagram that you look at when you have a 555 timer. This is the monostable configuration. As you can see, there are 2 resistors, 2 capacitors, and a trigger, which is basically just a tactile switch. This is pretty straightforward. The output just goes to whatever your output is. This 10 nanofarad capacitor is simply there so that your control input doesn't have any noise on it. It's basically absorbing any noise. This R2, this resistor, all it's doing is making it so that when you push in your tactile switch, that you aren't connecting VCC directly to ground. So the value there is semi-arbitrary, just enough to make it so the circuit doesn't burn up. And then that time constant that I mentioned is actually R1 and C. Now, I won't get into the details of how that's calculated, but your time constant of how high this circuit will be is 1.1 times R and C, R in ohms and C in farads. And so for our practical circuit, I actually chose 100 microfarads and 10,000 ohms. So we get a time constant of around a second. 1.1, 1.2 seconds, which we will see. But it's very, very straightforward. That time constant is simply 1.1 times RC, and it's this R1 and C that actually controls that. So this is not a great way to understand what's going on, so let's switch over to the other view where we will see what happens internally. So with the monostable configuration, what we have here is we have VCC going through R2 and going to the inverting input of this comparator down here. And we have the capacitor here. The voltage on this capacitor is going into the non-inverting input of this comparator right here. And those two things are absolutely crucial. Now here you'll notice that VCC is going to this inverting input right here. And since the switch is open, this gives us a low output because the inverting input is higher than our 1/3 VCC. So right now, our S is 0. Now also, because Q bar, and this is pulling from a previous state, due to the fact that Q bar is high, we are actually closing this BJT, so you have a high voltage to the base of this BJT, closing this switch, which is discharging this capacitor through to ground. So we have a 0 voltage to the non-inverting input to this comparator, which then gives us a 0 on the reset as well. And if you remember from your flip-flop truth tables, that means it's just using the previous state. And we'll get to how it gets to this state and how it, again, gets to this stable point. So with all of this, the output is 0 because this output right here is inverting the Q bar. So Q bar is high, our output is low. Our voltage on this inverting comparator input is high. Our voltage on this non-inverting input is low. So what happens when you push the button? If you push the button, suddenly you are grounding this inverting input. And so now that your inverting input drops to 0 and the 1/3 VCC is higher than the voltage here, your output that goes into S is now 1. So now our truth table is S is 1, R is still 0, but because if we look at our flip-flop truth table, Q bar now drops to 0. Now what this does is this opens this BJT switch right here and makes it so immediately you can start to get a charge through R1 to C1. It used to be that you would have that current flowing straight through R1 through to ground, but now it can go into the capacitor and fill up this capacitor. Now looking at this comparator right here, we are waiting for this voltage to hit 2/3 of VCC compared to this voltage divider right here going into the inverting. We're waiting for it to hit 2/3 VCC for this to flip and providing R, a high voltage, to invert the output of the flip-flop. So again, when you push the button, what you're doing is you are dropping this voltage here, making this comparator output a high voltage, making this S1, Q bar 0, opening up this switch, making it so that this capacitor is charging through R1, and the amount of time it takes for C1 to get filled via R1 to 2/3 VCC is the amount of time that it will remain low. Because what will happen next is as soon as you hit 2/3 VCC, the output of this comparator going into R is now 1, and suddenly our truth table, very briefly, is S equals 0 because we opened up the switch, we released the switch, and so this now is at VCC, so this is outputting a 0 again. R is equal to 1, Q bar becomes 1, and when it does so, it closes this and once again connects C1 directly to ground and discharges that capacitor immediately. So once that capacitor is discharged immediately, all of this flips again and R becomes 0 again, S becomes 0 again, but since for that brief moment it was Q bar equal to 1, once you have S equals 0 and R equals 0, Q bar is just dependent on whatever the previous state was, which was 1. And so now we're back in our stable configuration and our output drops back down because it is, again, the inverse of Q bar. So that is what's happening, is when you push that button, it charges the capacitor, and as soon as that capacitor reaches that certain level, it basically discharges itself and puts everything back to its original state of just having a low output. And it's pretty crazy how simple it is, yet how complex it is. And again, everything getting inverted and changing here and the flip-flop, changing states sometimes and not changing states other times can be quite complicated. But once you walk through this a couple of times, it should start to make sense. And hopefully having the truth tables of the flip-flop visible during the different states will help out a little bit. Okay, with that, let's actually get the oscilloscope set up and show this in action. So this is the physical setup that we're working with. Basically, we have our RC right here. This is the 10 kilo ohm resistor that I mentioned earlier, and the 100 microfarad capacitor right here. This smaller ceramic capacitor on the other side is simply that one on the control input so that we don't have the noise. And then over on this side, we have just a simple resistor that protects us from shorting VCC to ground, and I have my tactile switch right here. Everything else is simply to connect it to the power supply and to the oscilloscope, and also just so you can provide ground and power, and then pin 4 is also on power, which if I don't remember off the top of my head, but pin 4, I think it's pin 4, the reset to the flip-flop, we just want to tie that to VCC so that we don't accidentally get a reset. So that is the actual physical circuit that we're working with. Let's get this trained on the oscilloscope and see it in action. So on this, I have channel 1 set up as the output, and I have channel 2 set up as that voltage over the capacitor. So I put the oscilloscope into single shot, and we will see what happens as I push the button. Oh, no, there it goes quite nicely. All right, since we had a 100 microfarad capacitor and a 10,000 ohm resistor, we were expecting about 1.2 seconds. So as we look here, we have our 500 milliseconds per division. So we got half second, 1 second, and then yeah, we're at about 1.2 seconds. So this is exactly what we expected. Our output goes high, and then as we hit 2/3 VCC, the whole thing just resets, drops, and keeps on going. And if I push it again, we'll see if it triggers again. No, it won't, because I didn't restart my oscilloscope. So there you go, and I can even do it again and again, and you can see them over and over. I can just even have this thing run in auto mode. But yeah, that's basically it. That's all we have. It's something where you push the button, you get an output for a set amount of time, and if you want a longer time, you increase the resistance or the capacitance of your circuit, and you can make it so it lasts, honestly, as long as you reasonably want. There are limitations. You don't really want to get a resistor below like 1K, and if you get anything up in the mega ohms, you're going to start having problems. And kind of the same thing in the capacitance side, but it's generally pretty dang flexible. So that is what the monostable configuration looks like in its output in real life. Okay, so now we have gone over the monostable configuration. We went over what's going on inside and kind of the complexities of the different states and all of that. And I hope you found that fascinating. And we were able to see exactly how it works in real life, which is always very, very exciting. If you found this helpful, give it a like, subscribe to the channel, all that good stuff. Next time we will be doing the bistable configuration, where we're going to be learning more about what goes on internally with that, and also have a good example of how it actually looks in real life. I hope you enjoyed it. Have a great day. We'll see you in the next one.